All right, well, hello everyone, and welcome back to our lecture series on engineering mathematics. Today we're going to transition into the land of differential equations. Today we're going to be introducing how to classify differential equations and some elementary solutions, as well as the graphing techniques. So first off, what is a differential equation? According to the book, this is now the ZIL book. We're doing the 7th edition of Advanced Engineering Math. The definition of a differential equation is really just an equation that involves derivatives of some dependent variable or multiple dependent variables with respect to effectively independent variables. There could be one or more. That is what's called a differential equation, or a DE. What we do with these differential equations is we typically start by classifying them. So we'll classify these in a number of ways. Number one, we'll classify those by type. So I'll box this in here. And so, for example, an example of a differential equation is something like this: dy dx is the derivative of some function plus 6y equal to e to the minus x. Another example would be d squared y dx squared plus dy dx minus 12y equal to 0, and maybe dx dt plus 3x equal to 0. I can actually move these near each other. Move these over a little bit. Let's do dx dt plus 3x equal to 0. So 3 different kinds of what we would call an ordinary differential equation, or ODE for short. So these are all examples of ODEs. And what makes it an ordinary differential equation is that it has ordinary derivatives. So dy dx instead of what we say partial derivatives with respect to x. An example of a PDEs is if I did partial derivatives instead. So if I had partial squared u partial x squared plus partial squared u partial y squared equal to 0. Or for example, partial t with respect to, say, time t is partial squared t partial x squared. Or maybe partial u partial x. Let's do partial u partial y equal to partial v partial x. So what I would like to go through is what are the independent and the dependent variables, and that kind of screams at why it's a PDE versus an ODE. So for example, let's list the independent and the dependent variables here. So for the independent variable in the first equation right here, it's x, and we're thinking about y being a function of x. That's the goal, is to find what is y as a function of x, given this relationship, the relationship between the function y and its derivative, as well as x. In the second equation, similarly, x is the independent variable, and y is a function of x, is the thing we're looking for. And you'll notice in the last one here, the derivative is with respect to time. So t is now the independent variable, and x as a function of t is the dependent variable. If we do the analog over here with these partial differential equations, or PDE for short, we can think about there being now 2 independent variables, and there being a function u of xy, or a surface, that describes the solution of that differential equation. On the next equation, we think about x and t being the independent variables, and capital T as a function of x and lowercase t being the dependent variable we're looking for. And the last one's kind of weird. The 2 independent variables are x and y, because those are on the bottom of those partial derivatives. And we can think about each function possibly being a function of each because they're both listed with partial derivatives instead of ordinary derivatives. So now there's actually two dependent variables. This comes from something called Cauchy-Riemann equations in complex variables. The second one in here is something called the heat equation, and the first one is something called Laplace equation. And the first and the second one here we will touch later in the course. But what we're going to focus on initially with differential equations are the ordinary differential equations, where you have an ordinary derivative and typically one independent variable and one unknown function you're looking for. Okay, so that is how you classify via type, either as ordinary or partial. You may also classify a differential equation by the order, and this is typically what people do first, and the order is the highest derivative. So it's pretty straightforward. So for example, if I had d squared y dx squared plus 5 dy dx, let's say cubed minus 4y equal e to the x. Okay, this equation would be second order because the highest derivative in there is power 2 there. Notice that's different than the dy dx being cubed. For example, this thing, that's not the order, but instead that is the first derivative cubed. So it's a little deceiving. Notice this is a little different than, for example, if I wrote, I don't know, partial x, let's do 5 here. 5 plus partial squared u partial t squared equal to 0. So this is a PDE now, but we classify it, the order of it to be the same thing because 5 is the highest order here. We would call this fifth order. Okay. In general, again, like I said, we're going to focus on ODEs. So the general form of an ODE, it can be just some function essentially of the independent variables, the dependent variable, and all its derivatives, or some amount of derivatives, where, for example, you'd stop at whatever the highest one is. And essentially that function equal to 0 would be how you would write a general form of a differential equation. But I will mention that's not very helpful. Seeing a general form, it's like, okay, cool, we can write it as some function equal to 0. What we like to do is we like these ones called linear equations. So there's a measure of what we call linearity. And basically the definition of linearity is if an ODE can be written as the following form, then it's called linear. So first off, you have a bunch of coefficients. So this would be the highest derivative, which is called the nth power right here. And with some coefficient that's a function of x. No, that's not a function of y. And the coefficients have this index, n, minus 1, and minus 2, that decreases as we go through here. And eventually you would stop with, just the first derivative, and then with some constant, I think that's a sub 0, and then if that's equal to some function g of x, essentially, that is called a linear ODE. Okay. If it's not a linear ODE, it's called a nonlinear ODE. So as a few examples, y double prime minus 2y prime plus y equal to 0. Notice the coefficients are 1, minus 2, and 1. This is then classified as a linear ODE. This is different than something like, let's say, d squared y dx squared plus sine of y. Notice now, to get it in this form, the term by itself, which would have been this one right here, now involves a function of y here. So this guy makes it nonlinear. Okay. One more final example here. Let's say we want the fourth derivative plus y squared equal to 0. Again, this term doesn't involve just x, it's a function of y, so that makes that thing nonlinear. So it turns out that linear ODEs are at least our first thing that we're going to tackle, and the most kind of the best ones to do an introduction to differential equations. Nonlinear ODEs are much more difficult. And with linear ODEs, we can also classify this thing called homogeneity. We can classify, again, I'll mention this is only for the linear. And essentially, G equal to 0 in the above expression gives what we call it homogeneous. I'll make that a little clearer. There you go. And so to give you two examples, in this example, the 0 at the right-hand side is what makes it homogeneous. Versus if I were to write the same thing, I don't know, let's put x there. This guy right here would make it non-homogeneous. Okay. And finally, one way to also classify an equation, in particular the first order equations, is of the form dy dx equal to a function of y. So notice the right-hand side is a function of the dependent variable, but it has nothing to do with the variable x, or the independent variable. Some examples of this are, for example, dy dx equal to 1 plus y squared. Notice the right-hand side has no x's in it. Or, for example, dy dx equal to y. Again, these are two separate examples that tell us that these are both autonomous equations. If, for example, I put an x there next to it, that no longer would be autonomous. Okay. Let's talk solutions. So you may be wondering at this point, who cares about a differential equation? I would say most equations, a lot of equations from physics, that is, come from some kind of conservation law, momentum, mass, energy, which turn into a differential equation. A lot of variables are constrained by the relationship with their derivatives, such as velocity, acceleration. Newton's law, in fact, with F equal to ma, governs a lot of the differential equations that we know and love. But you might be wondering, like, what's a solution of a differential equation? So, for example, dy dx equal to y. Turns out that one possible solution is e to the x multiplied by some constant. And this is what we call a general solution. Okay, it's general because there are many different constants that make this true. So how do we actually prove? I guess I'll say prove. Well, I would take dy dx, and if I take the derivative of c times e to the x, it's actually just itself, c times e to the x, but that's actually the original function y. So I've indeed shown that dy dx is equal to y, like that. And I've proven essentially that it solves that differential equation. And visually, what we're seeing here is if, for example, if c equal to 1, so if c equal to 1, it would be the curve y equal e to the x. If c equal to 2, it would be the curve y equal 2 e to the x. And then if c were equal to minus 1, the terms would be negative, and so they would go this way. And if c equal to minus 2, they would go this way. Great. Okay, and I guess I should mention at this point that eventually these, it's a little deceiving here, but these all asymptote, so maybe the proper way to show this is like this. This would be c equal to 2, and c equal to minus 2, where the intercept is different in each case here. Okay, these are called solution curves. So solution curves, and it's a way of visualizing what the solution of a differential equation is. But how do we pick? How do we pick which curve we want to represent the solution? Because that's a general solution, we need to talk about something called an initial value problem, or IVP for short. And an example of that would be, take that differential equation that we had before, but give some kind of condition on the initial value of that. So notice that this is a ODE, and this is what we call an initial condition. It's initial because the first value you're plugging in is 0. This as a whole is called an IVP, an initial value problem. And what it does is it allows us to pick one of those solution curves. So one way of plotting this, is to do this thing called a slope field. Okay, and the way we do what's called a slope field is we write our differential equation, we write y, and we write y prime here. What we do is we pick a value of y, for example, 0. And if I plug in 0 into this expression right here, the left-hand side would also equal 0. So this is y prime. If I plug in 1, the slopes would be 1. And if I plug in -1, the slopes would be -1. So visually, what we're showing you here is, if I plug in 0, meaning along the line y equal to 0, all the slopes are 0. So a representation of the slopes are these little dashed lines. And the slope, the line with slope 0, it would kind of be the line y equal to x. Versus if I looked at y equal to 1, which is again a horizontal line, the slopes would now be 1. And a line with slope equal to 1 is like y equal x. So I can draw little dashed lines that represent a slope of 1 that sort of look like y equal to x. And a similar analog to that would be at -1, I could draw slopes that look sort of like y equal to minus x. And when we have the curve y equal to e to the x, that's the c equal to 1 case, that's the solution of this IVP above. Then what we're actually showing you is we are plotting a solution curve that looks like this. Okay, that satisfies the IVP. So what the IVP is doing is picking out a very specific solution curve, which is the solution of that differential equation, ODE, plus its initial condition. That concludes our lesson for today. Thank you everybody for watching.